if I can get Chris to come up here since we started about 15 minutes late. This is my friend and co-chair, Chris Glein, who is at Southwest Research Institute. He is a fan of the icy bodies. He was on the Cassini mission. He's on the upcoming Europa Clipper. And take it away, my friend. 18 minutes.
Thanks, Betty. I'm actually a fan of exploring outer space, not just icy bodies. All right, let's proceed, if this will work. Oh, there we go. Okay. Yeah, so today I'm going to talk about Saturn's moon Enceladus. I was really pleased to see that Bethany gave you all a sneak peek, and we'll really dive into Enceladus for this talk, and I'll discuss its importance in the search for life. But before getting there, maybe it goes without saying at a breakthrough meeting, we might want to ask ourselves, why is the search for life important? And I really think about this in two different ways. You know, there's kind of like the scientific answer to this question. We want to push the envelope of knowledge and ask ourselves, what is the role of life in the universe, or is life an inevitable outcome of the laws of chemistry and physics, where through science, we've learned to replace many of our origin stories with this new understanding of cosmic evolution, where you go, from the Big Bang, galaxies, stars, planets, and so forth. But as of right now, we only know on our planet that all of these processes have eventually culminated in life. And we like to know, is this common or maybe not? And then the second reason is more of the human side of things, or how we feel when we search for life. We feel excitement. We feel like we want to do something great. We heard this morning that we could be the first generation that's on the precipice of answering this question of whether or not we are alone in the universe. And what a gift for posterity that would be if we could answer that question. And then for me personally, there's just like the cool factor, right? So we are blessed to be given this opportunity to ask the big questions and to seek out life. And I'm a sci-fi geek here, so I really like that what I can do for my day job involves merging what we think could be possible with actual experiments to test what's possible. So space exploration has given us an embarrassment of riches. And many of you have probably heard of the candidates for where we might go to look for life. These are kind of like the big five, where we have 4 objects in the solar system and then huge numbers of exoplanets to study. In today's talk, I love all planets and moons, so I'm not going to put down any planets or moons. I'm going to focus on Saturn's moon Enceladus for 2 reasons. One, it has this amazing story to tell us for astrobiology. And the second reason why I'm interested in Enceladus is it's kind of like an underdog. So I'm an American, I like sports, right? And so we're always rooting for the underdog. Who's going to beat the New England Patriots, that kind of thing. And Enceladus is kind of like the underdog in our exploration to search for life, where all these other objects got all these great missions, either already studying them or we're planning to send missions. But Enceladus so far has flown under the radar. So I'm going to let you in on a secret of what we can do. First, I'll tell you a little bit more about Enceladus. I know Bethany mentioned it. It's a small icy moon of Saturn. It's one of Saturn's 7 major moons. I love that I'm giving this talk in the UK, because this graphic is finally very relevant. This is actually 2 scale shown here, so it's a very tiny moon. Europa, you've probably heard of Europa, Jupiter's moon, is roughly the size of our moon. These are the big moons. Enceladus is just a baby. It's tiny, right? But it packs a punch, and we'll get into that in a little bit. It's a cold moon. It orbits Saturn. It's 1 billion miles from the sun. It's very cold on the surface, near the temperature of liquid nitrogen. And it's also the most reflective object we know of in the solar system. It's covered by very clean water ice. I guess we can just stare at Enceladus for a little longer. Oh, and that just took the complete wind out of my joke here. So Enceladus should not be confused by things that might sound like Enceladus. That was a fail, by the way. So you probably heard, hopefully, or if not, you're in for a real treat here. We had this mission called Cassini-Huygens. It was a joint collaboration between NASA and the European Space Agency, and it discovered some really fantastic things in the Saturn system. I would argue that the biggest discovery, the most intriguing and surprising thing we found was that this little moon of Saturn is erupting a plume into space. And Bethany showed you, you can see the plume going out 200 kilometers. It actually goes out a couple thousand kilometers into space. You can really see it from the James Webb Space Telescope. This plume is massive because the gravity is so feeble on Enceladus. And what's really significant about this feature is by finding it, we've learned that Enceladus is the smallest geologically active body in the solar system. For all intents and purposes, this body should not be active. It should just be a frozen ice cube, but it's not. And we've learned, we did a number of flybys with Cassini. The last one was in 2015. We flew the spacecraft actually through the plume. And we had different kinds of instruments collecting data, and some of the instruments, known as mass spectrometers, which could measure the chemistry of the plumes, revealed that the plumes taste salty. So, there's frozen ice particles, and those particles actually contain salts in them. And from that discovery, we were then able to piece together what we think is going on. And the punchline here is we think that the source of the plume is a global ocean of liquid water, thought to be about 40 kilometers deep. So it's about 10 times deeper than Earth's oceans are on average. Pretty spectacular. Maybe we just have operator error here. Oh, there we go, okay. So finding all this water created a lot of excitement among the scientific community because on Earth, wherever we find liquid water, we find life. And so the natural question is, could Enceladus be alive? And to get to the bottom of that question, what we tend to how we tend to organize our thoughts is around this question of habitability. And what habitability is it's the ability of this environment to support life, to provide the essential ingredients that life would need to sustain itself. And in really general terms, you can boil that down into liquid water, and we found that on Enceladus. It has an ocean, right? And then there's these other two requirements, a source of energy that life can use to power itself, and then the key building blocks like organic molecules and other key nutrients. And I'm going to spend some time now going into these questions we had about whether Enceladus could provide these things. We designed a flyby. This is just near the end of the Cassini mission, late in 2015. We flew through the plume, and we were surprised to find a very large abundance of hydrogen, H2 molecules, in the plume. So you can see, this flyby happened very quickly. Within about 30 seconds is when we collected all our data. So the spacecraft was screaming through the plume. And then right near closest approach, we detected a massive spike in the signal corresponding to H2. We estimate it's about 1% hydrogen in the plume. For those of you who are astronomers, maybe this isn't so interesting because H2 is the most abundant molecule in the universe. But on a small moon, it matters to find hydrogen because the gravity is too low. Enceladus cannot hang on to H2, so it must be actively produced in the interior. And we scratched our heads for a while to try to understand what could explain this. And this is the mechanism that we landed upon, shown in this graphic here, where I mentioned it's covered by bright ice on the surface. We have plume erupting. There's a deep ocean there. And then we were able to use the chemistry of this plume to peer down into this dark hidden world down there. And we think the chemistry is telling us that there is hydrothermal activity at the seafloor. This very small moon. We think the water is reacting with hot rock. I won't bore you to death with all the geochemistry, but through water rock reactions, hydrogen can be produced. And eventually supplied to the ocean, and we see it coming out from the plume. So we think that this moon has hydrothermal systems. And probably the bigger implication of this finding was, again, from our knowledge on Earth, we've learned that when we visit these hydrothermal systems, we're astounded to find that life is actually teeming outside of hydrothermal vents. And the reason for that is because molecules like hydrogen are able to act as fuel sources to power their metabolisms and provide sources of energy in the absence of sunlight. So you can see this is a really great example. This is an image near a hydrothermal system in the Caribbean Ocean, where microbes feed on the hydrogen, and then shrimp and other animals feed on the microbes, and you have a full-blown ecosystem. Could it be on Enceladus? So this is the only boring part of the presentation, hopefully. I'm going to just give you a little bit of an introduction to how geochemists think about these kinds of measurements, because we can actually dig a lot deeper than just saying hydrothermal vents. We're able to quantify how much energy is available in this mixture of molecules. And we do this using this variable called the chemical affinity for this reaction up here, where CO2 reacts with hydrogen to make methane. It's known as methanogenesis. It's a very important microbial metabolism. And we can actually use the data from Cassini to figure out, is the system close to equilibrium, which is not too interesting because that would correspond to death, or could there be a source of energy that could be exploited? Here's how much energy microbes need on the Earth. They need 10 to 20 kilojoules to keep on trucking. And here's what we learned when we pieced together all the data from Cassini. We're able to then pinpoint roughly how much energy might be available in the system, and it's shown by this cyan region right there. And notice, this is above that, right, coming from a scientist. We can easily see that. And what that means is that the energy supply is greater than the demands of life as we know it. So we would conclude that this environment is energetically habitable. And a good way to think of how much energy is available is I calculate, this is a very difficult calculation, it's the equivalent of about 300 cheese pizzas every hour that is coming out of the plume. Not too bad. So we think there's a source of energy. And then the last topic I want to touch upon is the essential elements. This is our most recent story. It's published last year. The question of phosphorus. Phosphorus, and this will be a great lead into Jane's talk, it's really important for life on Earth. And as far as we can tell, no other element can replace its role in biology. It serves a number of roles. Probably the one we're most familiar with is it's a building block for our bones. But within the biochemistry of our cells and for microorganisms, phosphorus is super important in allowing energy to be transferred between different molecules. A classic example is known as adenosine triphosphate, ATP. So it's important. It might also be a biosignature. And in Earth systems, like our ecosystems, phosphorus is often a limiting element that restricts microbial growth. And on Earth, normally phosphorus is rare. It puts a lid on microbial activity. And people originally thought that, by analogy, maybe phosphorus should be rare in other oceans, right? We weren't quite sure a couple years ago because we know that the chemistry of Enceladus' ocean is actually a little bit different from Earth's ocean. So rather than just say it should be like Earth, we thought we should make some models to try to understand what might be possible. And it's summarized by these figures shown here, where this is published a few years ago now, where we made predictions based on the geochemistry that we know of Enceladus' ocean, how much phosphorus we might expect based on water-rock reactions at the seafloor. And that's represented by these bands shown here. So this is the predicted concentrations of phosphorus. And here's Earth for reference. And one thing that really surprised us was, for most cases, it seems like the predicted levels are either comparable or even much larger than what we find in Earth's oceans. So this created some encouragement for us to, again, dig a little deeper. So what we did is we then started working with some colleagues in Germany. They did some great work analyzing a huge number of data from the Cassini mission, and we focused on Saturn's E-rings. This is a ghostly ring around Saturn. And it's important because it's coincident with the orbit of Enceladus. And we now know that the plume actually supplies the E-ring. So the E-ring is composed of lots of plume particles that have escaped from Enceladus, and they've been trapped in orbit around Saturn. So in a way, if we sample the E-ring, we're able to sample what originally came out of Enceladus's ocean. It's a frozen reservoir of ocean water. And the team in Germany, led by Frank Postberg, they analyzed thousands of particles in the E-ring that were sampled by Cassini, and they found the needle in the haystack. This is an example of one of the spectra that were collected. This is a mass spectrum showing the masses of different species detected in the plume ice grains, and roughly they're abundant shown on the vertical axis. And you can see I've already simplified this by outlining this box shown here. These are new species that were seen for the first time, sodium phosphate species in the E-ring ice grains, showing that phosphate species are abundant in the plume. So that seemed to suggest that maybe we're on the right track with this model, and this is an environment that is rich in phosphorus. In fact, this is the first detection of phosphorus in an extraterrestrial ocean. And I got to tell you a little bit more about the chemistry, because I love chemistry. You might wonder, why is phosphorus so abundant in this ocean when our oceans don't have too much phosphorus? It's a great question, and here's how we can simplify it. It all boils down to the beautiful coupling of chemical equilibria between bicarbonate, which is one example of baking soda, calcium ions, and phosphorus. It turns out that if you have a soda ocean, like we think Enceladus does, what that tends to do is it drives down the concentration of calcium by a lot. And when that happens, phosphate minerals like apatite are much more soluble, and they naturally produce large abundances of phosphorus dissolved in the water. And if you don't believe models, you can actually go out in the field and confirm this for yourself. This is one example. It's of a soda lake. It's called Last Chance Lake in British Columbia in Canada, and it's the most phosphorus-rich body of water that's known on Earth. And people have made measurements, and you can see this is just one summary figure showing that as you have more carbonate, more soda dissolved in the water, phosphorus really shoots up. And there's where Enceladus falls on this kind of plot. So it's like a soda-rich body of water, soda ocean meeting these soda lakes. So we think, based on what Cassini showed us, that Enceladus has an extant liquid water ocean that is seemingly habitable. We found everything that life as we know it would need. The only thing that we're not quite so sure about is sulfur, and that's still work in progress. And I think we're just about out of time, but on my last slide here, this is a call to action for this community and others who might be watching online who are interested. Just to summarize, we have a body in our solar system beyond the Earth with abundant liquid water and other evidence for extant habitability. And not only that, but it's actually an accessible body of water. We can go there, we can land on the surface, we can fly through the plume, and we can sample material that came from this ocean. So it offers us a very unique opportunity in our solar system to look for evidence of life. The unfortunate thing about it is, like I said, Enceladus is our unsung hero. We don't currently have any concrete plans to get back there yet. Nothing has been funded. And this is a great opportunity for a grassroots effort to start building, to try to get to the bottom of this age-old question, is biology unique to Earth, or is it an inevitable outcome of the laws of chemistry and physics acting on matter in complex planetary environments? And with that, I think I'll be kicked off the stage. Thanks. Here's this.